Let's talk a little bit about gamma decay. Uh, the concept here is that the nucleus actually has energy levels. Okay, and so if you recall in the Bohr atom, right, we got the nucleus and we've got these stationary states, and when electrons made transitions, they gave off visible light. Well, if a nucleon undergoes an energy level transition, the energy is so great that it gives off gamma rays, which are just very, very high energetic photons, right? So that's the idea, right? Is that a gamma ray is a photon that represents the energy level between the upper energy level and the lower energy level. Okay, um, and so that's why the wavelengths are so short, because they represent a tremendous amount of energy. These are deadly. This is deadly radiation. Um, Usually, these things happen after a beta decay or an alpha decay, and so it's when the alpha decay occurs, it leaves some nucleons in a higher energy state, and they can move down to fill, sort of like fill the gap. It's sort of like Jenga. You pull something out from underneath, and everything makes a transition down sometimes, right? Um, and it can take a while. I mean, the alpha decay can occur, and it can actually take a little while for the gamma decay to occur after that. Okay, um, there are many energies possible. I'll show you this, but yeah. Okay, and then the idea is that gamma rays are actually stopped by, they're pretty deadly radiation. It takes meters of lead to stop some of them. And the idea is that you can actually sterilize food. Like if you want to get rid of the E. coli in ground beef, you just expose the ground beef to gamma rays, and it'll kill the E. coli. Um, what else it does to the beef, we're not exactly sure. So I'd rather have someone else try irradiated beef before I do for a long time. Um, Here's a picture of and these are energy diagrams of a decay. This is an alpha decay, and I know it is because it's going from a 12 to a 208. It's going down by 4, right? Um, and what tellurium was before it alpha decayed, right, is none of your business, right? Okay, anyway, the idea is that the alpha decay can leave this nucleus actually in several energy states. The most probable state is this one, right? The next one is this one, right? So, these are these things, right? And when it leaves it in this state, so those alpha decays that we figured out are like, when we figured them out, was going from this energy level to this energy level. But it's actually a little more complicated than that. It can actually leave this guy in a higher energy state, okay? Then see these little transitions. These are transitions. The energy difference from those is what's given off as a gamma ray. Okay, how do you draw gamma? Gamma. There's a gamma. Those are not so gamma-y, right? So these energy transitions, these are all gamma ray energies. Okay, those are all gamma ray energies, and so the thing that's interesting is that gamma rays are actually discrete. If you look at a graph of them and look at intensity versus energy, there are particular gamma rays that you'll get, right? Like this is a very probable one. This one's not so probable. These are, more energetic, less energetic. It's not just any energy, it's a particular energy, right? This is a beta decay, okay? Because notice that the mass number doesn't change, right? Okay. And again, beta decays can leave the daughter nucleus in an energized state, and the energy difference is released by a gamma ray, okay? So it's a little more complicated, but not much more complicated than we've let on here. Let me do an example for you. Okay, so let's suppose that we have plutonium, and it goes from this state to this state, right? In other words, so you can see that this is less mass, right? What's the energy of the gamma ray emitted? Well, this is actually pretty easy, right? We're going to compare left side mass to right side mass, right? Is 239.052464 U's, right? The right side mass is 239.052157 U's, and you guessed it, we're going to subtract those guys. Okay, 239.052464 minus 239.05 52157. Boy, that's a lot of typing of numbers. 52464, 52157. And I get, oh bless this thing, mode. How about normal mode? Enter, clear, second answer. It's still writing it that way. Okay, so it's 0.000307 U's. Is that right? Yeah, I think so. 0, 0. Yeah, that would make sense. Okay. And then, again, we're going to do the same thing. We're going to multiply by 931.5, just like we did with alpha decay. So times 931.5. And I get that the energy is 0.2859705. And we only have 4 sig figs. So let's see, 1, 2, 3, 4. So I guess we have to round it this way. Yeah? Yippee skippy. So that's just an example. We do the same thing that we always do.